Welcome to this 20th and last lecture of this course on RF filter and amplifier design. We have seen various amplifier designs, and in last two lectures we were discussing about power amplifiers, particularly the nonlinearity. So, power amplifier design is nothing new from the other amplifier designs for a gain etc., but we need to find out that what is the dynamic range where we need to operate the device. So, we have seen the concept of 1 dB gain compression point, we have seen the concept of the danger of third order intermodulation product, we have seen the third order intercept point, and based on that we have characterized the spurious free dynamic range. Now, we need to find out how to measure that spurious free dynamic range or third order intercept point, that we will do now. So, the question is, can the third order intercept point, output intercept point POI P3 and 1 dB gain compression point, can they be measured? Please remember in this title this dB, that actual thing should be like this dB, but in the PowerPoint this problem comes, I think. Now, the problem is like this, that the two tones, let us say of strength minus 20 dBm each, are applied and their frequencies, let us say at 2 gigahertz and 2.01 gigahertz. I said at the previous lecture that in two tone test the two frequencies, they are distinct, 2 gigahertz and 2.01 gigahertz are distinct, but they are not far off because they should be in a band. So, let us say 2 and 2.01, which means that it is already separated by 10 megahertz, and they are applied to an amplifier with 10 dB gain. Now, connect the output to a spectrum analyzer and following observations are made. You see that this is the way of measuring this third order intercept point POI P3. Oh, there is also another mistake, that POI P3 should be there, that in the title, because this is the third order intercept points symbol. And now, let us see that connect, you need to apply these two different tones, let us say of these two with minus 20 dBm power, and amplifier is of 10 dB gain. Now, connect the output to a spectrum analyzer and let us say make this observation that at 1.99, you know, spectrum analyzer means already we have covered spectrum analyzer in details in one of the earlier NPTEL lectures. So, we have frequency here, we have the power spectral density here, you can have it in power spectral density watts per hertz. So, now, there you measure what is at 1, you will see there are 1.99, there is one day, because 2 minus 2.01, 2 minus 0.01, that will be this 1.99, there is another at 2, there is another at 2.01, there is another at 2.02, and the spectral power amplitude. Oh, here you can also have in the y axis the power amplitude, that is in dBm. So, you have measured that. In spectrum analyzer you can change this. So, if you put it in power amplitude, let us say that the values are these. So, from this you will have to determine what is POIP, how will you do that. So, let us say this is the arbitrary point of measurement, and here we have shown that this power of the F1 component minus power of the intermodulation, third order intermodulation thing. So, at this point you see this is my Pf1 and this is also this is my P2F1 minus 2F2. So, this point is this. Now, I know this difference in these two, and from this slope I can then relate, because I know that this slope is of a slope 3, this is of a slope 1. So, I can find out this point. Basically, I need to find out this point. So, that point is PIP minus P2 F1 minus F3, and this point is 1/3 like this. So, the simple mathematics will show you that PIP is nothing but Pf1 plus half of Pf1 minus this, and then we can find out that what is in our case 2F1 minus F2 is 2 into this is 1.99 gigahertz. Pf1 power at frequency 1 is minus 20 dBm, power at 2F1 minus F2, that means at 1.99 we have read the value minus 70. So, PIP we can find out as this 5 dBm. So, P1 dB we know that 9.6, which I have said to be roughly 10, but actually it will be 5 minus 9.6. So, that will be roughly to my minus 5 dBm. So, now I know this. Also, you see that if I have a cascaded system, 2 amplifiers or one amplifier, one mixer, etc., and they are cascaded. Let the first system has gain G1, the intercept point PIP1, this has gain 2 G2, intercept point 2. So, we know that their overall gain will be G1 G2. Let us say their overall intercept point, third order intercept point is PIP. Now, unlike noise, IM products are deterministic, please remember that. So, voltage will add. So, voltage of IM3 product, that will be simply added, it is deterministic signal. Now, cascade of IP3. So, we know this is the dB relation, in absolute relation this is this. So, what is the voltage corresponding? I can relate that with a characteristic impedance Z0. From this I can find out the voltage. Worst case distortion voltage at second stage is this. So, also this is the another the power for second order second stage. Now, cascade you continue. So, you write down overall system I have this, and from individual one we have previously written these voltages. So, now I can relate, compare, and that will show you that overall intercept point will be this plus this. So, when second stage has no IM3 distortion, that means PIP2 if it becomes infinity, that means at very high value the intermodulation product will catch up. So, that means it has no IM3 distortion. So, if we put that, then PIP becomes G2 PIP1. So, this relation transfers PIP between input and output of a RF block. You see that the from 1 to the overall. So, that we can transfer the PIP between input and output. Example of a cascade PIP, the LNA has a gain of 20 dB, let us say, and then YP3, this is output intercept point of 22 dBm. The mixer, which is the next block generally after the LNA, has a conversion loss of 6 dB. You know, mixer always has a conversion loss because it is a nonlinear system. So, in conversion because it is changing the frequency it is converting, in that it always suffers a loss. Let us say that loss is 6 dB and an IIP3 of 13 dBm. Find the intercept point of cascade. Generally mixer specification, this is another industry does it like this, that mixer specification is in terms of IIP3. Amplifiers are generally use output intercept point, mixers are input intercept point. Now, transfer mixer intercept point to output, we have just seen that relation that can give you that YP3 mixture we can find like this. Now, amplifier is also output side, mixer is also output, we have converted that. So, now you can find out that gain is this. So, overall PIP3 from that formula is this 6.4 dBm. So, composite PIP you see is much lower than LNA PIP. Why? Because mixer actually determines nonlinearity. Actually, even though we have large signals case, but mixer it determines always the nonlinearity. So, composite PIP is much lower. This is important because in the overall system you need to find out the nonlinearity. So, even though single mixer it has quite good amount of nonlinearity, but due to the presence of LNA you have this relation. Also remember that this relation is not in dB scale, that previously also I have said, I think. Yes, you see that this relation is in absolute scale. You see all these in derivation we have used it to absolute scale. This is the not in dB scale. You can convert it to dB scale if you want, but as it is, this relation is in dB scale. Now, effects of nonlinearity. You see that this intermodulation product, third order intermodulation comes into play in transmitters only, though this example we have shown for LNA mixer, but there this nonlinearity does not come, but mixer is inherently an nonlinear device, that is why we have talked about that. But generally in transmitters, in the power amplifier stage, the final stage, this comes. Now, a cellular phone base stations, they transmit typically 30 to 40 dBm power. So, there is chance of nonlinearity, because they in these levels you cannot say it is a small signal level, and there for GSM standard the guideline YP3 is that you should have your output intercept point below minus 125 dB. Similarly, also satellites, suppose satellite base station, when it satellite ground station, when it sends to the satellite the power amplifier, it is a huge power amplifier, megawatts of power it sends. So, that time also you should specify in that power amplifier what is the YP3, what is the spurious free dynamic range, etc. So, similarly from the satellite, when satellite in its transponder it sends, there also there is this YP3 or IIP3 it specifies. Generally the power amplifier they specify YP3. So, you need to specify YP3 for any power amplifier, and this is the way it should be calculated. Also you remember that due to this nonlinearity, there is a always whenever there is nonlinearity, you are having an amplitude modulation signal, amplitude modulated signal gets converted to another amplitude modulated signal. That is why we get 1 dB gain compression, because you see what was the input side amplitude modulation, when due to nonlinearity we have seen that all your the gain things that gets changed. If you consider the third order intercept point, your gain gets changed, and that is why that characterization, this AM to AM conversion is 1 dB gain compression. Whereas, there will be when you are changing the system, when you are squaring, basically you are changing, playing with the frequency. So, there will be change of phase also. So, you get a AM to PM conversion, change in output signal phase due to fluctuation in input signal amplitude. It is for phase modulated signals, it is serious, cannot be that this thing cannot be predicted by power series scalar model. In our model, what we have seen, we can predict this M to M conversion, because we have a system model, but you see our system model is this. This was our model which we used, that VO is equal to A1 V in plus A2 V in square plus A3 V in square. Now, here you see this V in square, V in cube, all this basically we are assuming V in the amplitude part of V in, and this A1, A2, A3 they are, we are assuming scalar quantity, but even if we make them vector, this V in, then V in we should consider as a phasor with both amplitude and phase. If we do that, then these expressions won't be simply their square, we will have to use that conjugate relation and we will have to consider. So, we should have A1, A2, A3, all of them should be vector quantities or phasor quantities, and this V in also, when we are squaring, we should remember that we are squaring a complex number. So, appropriate that mathematics we should bring. If we do that, then we can find PM. That is a more complicated model. At your level, you do not require. In the MTech level, we do not expose you to that. When you do research, you can consider these as complex phasors, and then you can find out this. So, but you remember that there is a phase modulation when we have nonlinearity, because you are changing the when your input signal is fluctuating, you see V in is changing, you are squaring it, cubing it. So, that is changing the phase of the output signal. So, with that, I think we have covered the whole series of this RF filter and amplifier part, their analysis, their design. Hope this knowledge will help you. Hope you have understood this concept, and then you will start designing your amplifiers and filters, RF amplifiers and filters, microwave amplifiers and filters. Obviously, the more and more you design, more and more you do practical designs, you get better insights. And also, I have always tried to emphasize that design means it is an open thing, it is also part of art. So, where you will put the source impedance, where you will put the load impedance, that more from your practical design experiences you gain. This theoretical background helps you to understand that okay, this is your playing ground, but how you play, that is how you practice. So, practice more and more all this RF and RF filter and microwave filter, RF amplifier, microwave amplifier design. I hope you will enjoy this throughout your life. Thank you.